Hi class. Today we're going to look at solving the constraint optimization problem using Lagrange multipliers. If you look back at the worksheet you got on Tuesday, the end of the worksheet had the example f of xy equal x plus y. And first one was just looking for the maximum of that function over the plane R2. So here we have a picture of the plane. We've drawn the level sets of f. Ignore for a moment the circle. We'll come to that next. When we look at the level sets, what we see is that as we go up in the diagonal, the values of f increase, and they just keep increasing forever. So this f function has no global maximum, and if we look at the decreasing values, down to the bottom left diagonal, it also has no global minimum. Here we see that. So to begin with, just on the plane, f does not have a global maximum or global minimum. Now we say, though, just look at x's and y's that lie on the circle, x squared plus y squared equals 1. Out of those x's and y's, does f have a maximum value and a minimum value? We'll focus on the maximum, but a similar type of argument will help for the minimum. So looking at the picture, f equals 0 is just in the middle of the circle. We can move to the right to f equal 1. We're still intersecting the circle. Here we do it at these 2 points. We can keep moving a bit to the right. F gets bigger, and then the last time f, or the line, touches the circle, that's going to be where the maximum occurs. Once x gets a little bigger, like f equal 2, it's no longer touching the circle. Another way to say this is that the circle is a closed and bounded set. It's bounded because it lies in a finite region of the plane, and it's bounded to find out if it's closed, we say, let's look at endpoints or boundary points. But because it's a complete closed circle, there are no endpoints. So since there are no endpoints to worry about, we could say that whatever endpoints there are in the set. There aren't any endpoints, so there's really nothing to check. But that leads us to conclude that the circle is a closed set. And then because it's a closed and bounded set, the continuous function f will have a global maximum and minimum. That was our big theorem. So let's find exactly where those maximum and minimum occur and what their value are. And we have this picture that as f increases, it's intersecting the circle first at 2 points, but then eventually just at 1 point and then at no points. And the maximum of f will occur at that 1 point of intersection. Another way of saying that is that the f level set, the straight line, is tangent to the circle, and that's where the maximum will occur. So the maximum value of f on the circle occurs when the level set of f is tangent to the circle. So our focus will be, how do we find out when that tangency occurs? And we're going to turn the problem around a little bit, and instead of looking at tangency, we're going to look at the normal vectors. So in this picture, first we have a line going through the circle. This could be the f equal 1 level set, for example, intersects the circle twice, And at this point on the side, I've drawn the perpendicular or the normal. NG is the normal to the circle, and NF is the normal to the tangent line. And at this first line, those vectors are pointing in very different directions. Let me just put a little perpendicular. So for the circle, to figure out the perpendicular, that means I have the tangent line to the circle, and the perpendicular is at 90 degrees to that tangent line. Now the second case is when the level set F is tangent to the circle, and in that case the NG, the normal to the circle, and the normal to the F level set are pointing in the same direction. Since their tangents are the same, that means their normals will be the same. Well, they'll be in the same direction, I should say. They are not necessarily the same vector, because one could be longer than the other. That's what we see here in the picture. So we've come to this conclusion that we're looking for a point where the normal to the G. So I introduced the name G to represent the circle. So we can think of the circle as G of xy equal x squared plus y squared equal 1. So the circle is also can be thought of as a second level set. There's the F, which has its level sets. That's what we've been studying all along, the different level sets of F. But we're going to start thinking about the circle, the constraint, as a level set of a new function that we're going to call G. So now we want the normal to the G set to be parallel to the normal to the F. We know that if two vectors are parallel, one is a multiple of the other. So we're going to say that NG is some constant times NF. And it's traditional to call the constant lambda. And we know how to get a normal to a level set. Here's kind of the punchline. If we can have a small drum roll, please. Thank you. The normal to a level set is equal to the gradient. So that's del f, which is f sub x and f sub y, the partial derivatives. Similarly, we can get the normal to the constraint set if we think of it being the level set G. So its normal is gradient G, which is G sub x and G sub y. And now our parallel condition translates into the normal condition that the normal to the G curve is a multiple lambda times the normal to the F curve. The normal to the G curve, we said, is gradient G, and the normal to the F curve is gradient F. So we have the equation gradient G is lambda times gradient F. We don't know what lambda is. Lambda is an unknown that we'll figure out as we go. And it's also called the Lagrange multiplier. And this method we're doing is called the method of Lagrange multipliers. And this gets used in economics, and that's where the term Lagrange multiplier comes from. So if gradient G is lambda times gradient F, and we write gradient G as the two partials gx comma gy is equal to lambda times fx comma fy, the first parts of the vectors have to be equal, and so do the second part. So that means gx has to equal lambda fx. That's one. And the second equation is that gy is equal to lambda fy. So we're going to have to solve those two simultaneous equations. But also we have a third equation, which was our constraint from the beginning, that g of xy, which is the x squared plus y squared, that equals 1. So we're really going to have to solve these three equations, and the global max and the global min will be the solutions of this system of three equations. So now let's look at our example and set up these three equations for our particular example. So in our example, g sub x is 2x and g sub y is 2y, since g is x squared plus y squared. And f is x plus y, so fx is 1 and fy is 1. Now we have our three equations that we need to solve. Gx equals lambda fx. That becomes 2x is lambda times 1, or lambda. Gy is lambda fy, becomes 2y is lambda. And then the constraint g equals 1 means x squared plus y squared equals 1. If we solve the first equation, we get x equals lambda over 2. Solving the second gives y is lambda over 2. We plug those two values for x and y into our third equation, the constraint, x squared plus y squared. So that becomes lambda squared over 4 plus another lambda squared over 4 equals 1. So that becomes 2 lambda squared over 4, or lambda squared over 2 equals 1. Cross multiplying gives lambda squared is 2, and square rooting gives lambda equals plus or minus 2. So these are the values of the Lagrange multiplier. So we're going to do two cases. Actually, one will give the global max, and one will give the global min. If we take the positive square root, lambda equal plus square root 2, since x is lambda over 2, it will be root 2 over 2, or 1 over root 2. Similarly, y is lambda over 2, so root 2 over 2, or 1 over root 2. So our first point of interest is 1 over root 2, 1 over root 2, and the value of f there, which is x plus y, is 1 over root 2 plus 1 over root 2, which is 2 over root 2, which is root 2. Now we do the whole same thing again for lambda equal minus root 2. If you do your calculations, you'll get x is minus 1 over root 2, and y is minus 1 over root 2. Plugging that into the f, which again is x plus y, we get minus 2 over root 2, which is minus root 2. And our global max and global min have to happen at these 2 points where we had the tangency. Remember, that was how we came up with the Lagrange multiplier formulas. And here is the 1 over root 2, 1 over root 2 point. And down here, if I roughly draw my axis, is the minus 1 over root 2, minus 1 over root 2 point. And so the maximum is root 2 on the top. That's the global max. And down on the bottom, that's when f is the minus root 2 down at that point. And that's the global minimum. So this shows how to do this method of Lagrange multipliers to find the global max and min when we're restricting f to some type of constrained set. In this case, the constraint x squared plus y squared equals 1 means we're only looking at values of f on the unit circle. So thanks very much. I hope this was something you could follow. Feel free to relook at the video, pause the video whenever you want. Thanks.